Hello all, just bear with me while I sort out some technical difficulties. Just give me a few moments and I'll be back in a moment. Well, I can see it on YouTube and I can see it on Facebook, but why? Why is it not working on LinkedIn? Just bear with me a few moments, please. It should be starting to appear on LinkedIn, but I'm not sure. Something is happening, so please go and grab yourself a fresh drink, whatever you need to do for a few. I'm probably going to be another couple of minutes just sorting this out. So I must apologise, just bear with me. Right, let's see if this works, shall we? So let's see if this works. Right, so now it's doing something with LinkedIn. Maybe, hopefully. Come on, LinkedIn. This is live, this is live broadcast. Don't work with children, animals, or LinkedIn live stream. Right, it says it's doing something, but I can't see it on LinkedIn. Why is it not coming through? Come on, LinkedIn, what is wrong with you? It looks like you're running late. I know I'm running. Why does it keep reset? Right, should I abandon LinkedIn or should I give it warm? Oh, something's happening. Here we go. Is it working now? Something's happening, everybody. Please, if it's working for you, please type in the chat. Let me know that it's working for you, that you can hear me. In fact, let me type where are you watching from? I'd love to know where you're watching from. So please type in the chat where you're watching from, how excited you are or not about watching this live stream today. And I'll give you a bit of a catch up of some of the things I've been doing over the last couple of months, because it's been a while since I've done a live stream. Don't worry, I've not forgotten about it. I've not forgotten about you. I've been doing quite a lot of the last couple of months. So I think since I last did a live stream, that was in April. So since then, I've been to Prague to the European Stamp Workshop. That was very exciting. Hi, Nick. Great to see you. So let's see if that works. There we go. Look at that. Nick, thanks for that feedback. I really appreciate it. It's great to see you. Great to have you on. So since we last did a live stream, I've visited Prague in the Czech Republic to attend the European Stamp Workshop. That was fantastic. It was great to see everybody. It was just great to see these presentations as well. It was, Prague is one of my favourite cities. I highly recommend it. The last time I went was in 1998, so that's showing my age. And it was very different. There was less Skoda cars on the streets this time. So that was interesting. But yeah, great city. I'd certainly recommend it. The next European Stamp Workshop, there are things going on behind the scenes, I understand, and the next one will be announced at some point in the future. I'm not privy to that information, so I can't sort of share any secrets or anything, but rest assured I'll be going to the next one. I've also been out to the Netherlands, to the European Space Agency, their technical headquarters, where I was working with Professor Riccardo Patriarca from the University of Rome Sapienza. So we were together working on a project for planetary protection, and we were presenting our results and did a presentation and some training for the European Space Agency. That was really interesting, really exciting. And then also you'll have probably seen from some of the pictures, I've been out to the US, but I can't possibly tell you what that's all about. Suffice to say, it was very exciting, very interesting, and I feel very privileged to be involved in those organisations to help them on their journey get some benefit with STAMP. So today we're going to talk about the Boeing Starliner spacecraft that had some propulsion, I can't speak today, propulsion anomalies on orbit. This investigation report was released by NASA early part of this year. And so we're going to continue going through that. There are a raft of other videos on my YouTube channel of all the other live streams I've done with regards to this. And my general intention is, once I've got through this live stream, I'm going to run a live session, a live get-together, a live Zoom, where we can get together live and talk to each other in a closed environment. And we can talk about this case study and any questions you've got about STAMP, STPA or CAST. Now, my intention today is essentially spend about an hour, about 90 minutes or so, going through the investigation report, making progress. And then depending how far we get today, we'll decide how many more of these live streams I need to do before I'm ready to do an actual workshop together. And of course, if you've got any questions, comments about the content or about STAMP, STPA or CAST, you're welcome to send me a message on LinkedIn, search for my name, Simon Whiteley, or go to my website, whiteley-safety.co.uk. I'll just bring that up on screen so you can see. Let's see if my buttons work. There we go. Slides, full screen. There we go. Look at that. Amazing technology. Yeah, if you go to whiteley-safety.co.uk, click this green button right at the top, really prominent. Just click on that link that way. Put your name and details in, send me a message, and I'll see how we can possibly help. So yeah, with that said, if you would like to type in the chat, let me know you can hear me in your location. That would be awesome. So Nick has said that he is in Cumbria. There we go, fantastic. I hope the weather's nice. It's been a bit wet on and off today with a bit of bright sunshine and a bit of rain. So fantastic. Great, here we go. Let's. So we've got some viewers on LinkedIn. Hello, viewers on LinkedIn. Have we got some viewers on YouTube? Let's see. I can't see because my window is too small. Yes, we have. Hello to everyone on YouTube. And then we've also got some in Facebook as well. So hello to everyone on Facebook. Right, so here we go. So this is the official investigation report. As I mentioned, it is quite a large report, 311 pages. So I have bitten off quite a lot to chew. So this is a bit of an elephant eating an elephant by live stream by live stream. This report was provided early part this year, February, by the investigation team. And it's kind of three reports sort of compressed into one. So there's the main investigation team, and then there were two other investigation teams looking at different but complementary topics. So they're brought together in this report. So it's not just one report. There's kind of summary from all three. So we've got Thomas. Thomas says Sweden here. Hi Thomas, great to see you. Thank you for coming along. So yeah, and in terms of the investigation report, so we got through the scope of the investigation in one of the early live streams. Additional investigations, so they're the other two investigations that are reported in here as well. It's important to understand that those investigations are ongoing, I understand, possibly even today. And I'm not sure whether the results from those investigations will be formally released or anything like that. I'm not sure. They'll probably be quite sensitive. Then there is the commercial crew program background. And then section 4 is by far the biggest section. And this is about the technical root cause analysis findings. And so we're going to continue going through this section today and talking about some of the challenges. Now, just to emphasize that there is, four main parts of the technical root cause analysis. The first is about the command module reaction control system jet failures. Then it was about the loss of the 6 degrees of freedom control, so the service module reaction control system jet failures. Then there was a helium leak, an analysis of a helium leak, and then an analysis of the deorbit capability fault tolerance, and then some common observations and organisational factors. So let's just jump across there. Then there's a discussion of the culture and decision-making process during the mission, and then there's a summary of the root causes, additional observations from the team, consolidated recommendations, and then of course there's 2 fault tree analyses that are included in this report, one for the helium fault tree and one for the service module reaction control system. Now because these are PDF files, the quality of the images of those fault trees is pretty vague, pretty difficult to read. So it's kind of difficult to learn a lot from those, but we'll see what we can do. But also be mindful that organisations are probably not going to want to put, technical or detailed fault trees in their publicly available reports because they are sensitive technical data. And of course, you don't necessarily also want the audience to misinterpret them if they don't understand how fault trees work and how to do them. So that's important. Then there are 9 appendices, so human factors, analysis of the survey data, some references, the acronyms, tables and figures. Just a point on the acronyms, tables and figures. When you're doing your own stamp-based analysis and building control structures, the acronyms, tables and figures is usually quite helpful because the acronyms list, as with all technical, complex technical systems and organisations, there's always going to be loads and loads of acronyms. And I'm sure Nick, involved in the stuff that he's involved in, and and Thomas as well, you'll understand that there is a lot of acronyms, and often there are the same acronyms that mean very different things in different contexts. But when looking at the acronyms list, you can identify potential candidates for inclusion in your control structure models as controllers, candidate controllers. Then there is the organisational test plan, the investigation team chartering memo, the commercial crew program, STAR SDRT report, and then the Boeing root cause corrective action analysis summary report, and then the senior review panel response to the investigation team report. So this is a big report. There is a lot in there. So if you do have the pleasure of reading through it with me, then let's go. Let's do it. So let's jump back then. Let's have a look. So where did we get to? There we go. Right. So we got all the way over to there, which is hardware. Section A. So section 455 fault tree, and that is split into I think 3 sections. So there is software. So we talked a bit about that last time. You'll notice just to prompt your spidey sensors, there is mention there of sensors failures, computer failures, and then software design flaws. So it's important to appreciate that software itself doesn't strictly fail. It is the context within which it is executed. So on a computer, the computer could suffer hardware failures perhaps, or issues with the hardware that influences the way the software executes, the way it behaves. And then of course software design flaws. There could be a flaw with how the software has been designed and how the software is then implemented on the hardware. and the architecture of those computers and data flows and all of that good stuff. So then we've got hardware. So we talked about sensors, computer hardware, software design floor. There we go. Let's keep moving this way. Inadequate thruster, fail off, FDIR, hardware. So incorrect oxygen flow. I think that's where we got up to. Yes. So let's start here. Let's start talking about hardware. So as I mentioned, these fault trees are, well, they're essentially blurred. I don't know if I could maybe stick it through an AI. You know, that's what all the cool kids are doing these days. Maybe stick it through an AI and see if it could enhance the image like they do in all the spy films. Maybe, maybe not. Some of them we could maybe make out. I think that one there says thruster, perhaps. Don't know what that says. That one looks like it might be pumps or something. But yeah, so it's a bit difficult to read this. And of course, the links in the PDFs, they don't work very well. So let's just have a look. What page is this? Page 43. Let's go to page 43 in the official report. Let's fingers crossed. Let's see if the hyperlinks work. And no, of course they don't. So yeah, just a polite observation. If you're writing an investigation report that's going to be made available to a population of people, it's really handy to make sure that your hyperlinks and things work, because otherwise it kind of undermines the trust in the report and the people doing the investigation and writing the report. Okay, so here we go. Let's have a look. Incorrect oxygen flow, B1. The incorrect oxygen flow branch of the fault tree addresses... right, okay, so B1 is this bit here, which I've handily already put a mark around. There we go. I'm anticipating myself here. Right, the incorrect oxygen flow branch, which you'll notice has 1, 2, 3, 4 high-level events. And then, I mean, that's a single, you could argue that's a type of base event, that one there. And then you've got 3 others. Some of them are red, some of them are yellow, some of them are amber. The incorrect oxygen flow branch of the fault tree addresses the insufficient fuel flow reaching the combustion chamber. This is caused by insufficient pressure, leakage, or so insufficient pressure. Let's just start using some pens. Everyone likes some pens to underline things. Here we go. So insufficient pressure, leakage, or an unstable oxygen state, causing an interruption to the reaction occurring within the combustion chamber. The fault tree branch is divided into 4 branches, which we can see there. 1, 2, 3, 4. Yeah, okay. B1 point... okay, so these are the labels for those branches. So we don't have to worry about the quality of the diagram. It's written in the text. Fantastic. So insufficient inlet pressure is this one, I'm assuming, going left to right conventionally. Leakage, non-helium leakage, blocked or reduced flow, and unstable oxygen state. So you'll notice 1, 3 and 1, 4, these two, these are highlighted in red. So there's likely to be some detail in this report that addresses those 2 gates. So insufficient inlet pressure addresses whether there was the necessary pressure for the propellant to reach the thruster. Just bear with me a second so I can stretch this and see what everyone's typing to me. There we go. Addresses whether there was the necessary pressure... I'm pressing on the wrong screen. There we go. Addresses whether there was necessary pressure for the propellant to reach the thruster. So before we continue with that, just have a little think for a minute. This is one of the things I always say in my training. Always, just have a think about what is the control loop that we're thinking about in this particular situation. So in this case, we're talking about insufficient inlet pressure. Hang on, let me just move this down here so you can see it. So insufficient inlet pressure addresses whether there was the necessary pressure for the propellant to reach the thruster. So we could say, if we're talking about propellant to reach the thruster, we're talking about some kind of controller that controls the propellant, and that controller provides the propellant to the thruster. The control process is the generation of thrust control, if you like. But between the actuator and the control process, there is going to be some form of actuators, some kind of valves perhaps, in this case. But there may also be some kind of sensory feedback. So is that feedback about the control process itself, or is it about the state of some of the valves? Is there some valve sensory feedback that goes into the thrust controller that we might want to think about? So I'm just sort of priming your mind. This is a jigsaw piece. Keep it in your mind, the control loop. Whenever we're trying to think about things, we're trying to think about things through the lens of this control loop and how it all fits together. And when we do this, what it does is it helps us to spot potential gaps in what we're looking at, but also gaps in our thinking, our consideration. It forces us to really think about, well, what is this control loop? And is it an open or closed loop? What are the parts in that loop? What are the specific control actions? What are the actuators we need to think about? What are the sensory feedback that we've got? And in this case, it's a question of, well, is it just feedback about the control process, or is there also feedback around the actuators themselves and the actuators' performance? So just keep that in mind. Nick is saying something. What's Nick saying? Let's have a look. What's the best way, Simon, to brief across complex FTAs to the uninitiated? That's probably a whole hour conversation in its own right. I suppose the first thing is just, have a think. What is the top event? Does it sound like a reasonable explanation of a real situation? And in this case, we're talking about post-accident. So we're not talking about trying to anticipate events and hazards. We're talking about what they think happened. So does that top event sound reasonable? Does it make sense? Does it sound logically complete? Are there any things that might be missing that we need to think about? And then moving down, the next layer down below that top event is, well, what is the spread of, next level events? And does that cover everything from, if you use the method primary, secondary and command when you're building your fault trees, such as, are there any primary failures or any second order failures that are not directly related but have an impact? And are there any command related issues? And the command related aspects very much closely align with when we're doing an STPA or a cast analysis, thinking about these control actions. So who or what is the commander so to speak? Who or what is the controller? What are the commands? What are the control actions they can provide? And what are the different ways that those commands, those control actions can be provided in a way that's going to upset our situation, upset our system? Now, of course, a fault tree is typically focused on failures, not necessarily successes. So the system is supposed to provide a particular control action in a certain context. But again, it depends how complex your fault tree analysis is, how much time you've got and how competent your analysts are. Now, of course, in certain organizations, if there isn't much time to do fault trees, often they focus very much on basic failures, and they align, and the gates and events and the structure very much aligns to the bill of materials or the components considered in the fault tree, in the failure modes and effects analysis. So again, we have to be a bit mindful as to what is the context, organizational and project context around a particular fault tree analysis and how it's been developed. Because if there's not much time and the people involved in the analysis, don't have access to the subject matter experts, it's almost certain that the fault tree analyses that you've got to review is going to be limited and perhaps missing some key things. And that's one of the things I really like about the STPA, the stamp-based approach, because when you start thinking about things through the concept of this control loop, you could start to spot logical things that are missing or potentially missing from the fault tree analysis. But of course, we have to be mindful that a fault tree analysis is not intended to capture the things that that STPA and CAST can find. Because again, STAMP, STPA and CAST, they can not only find failures that lead to accidents and losses, but they also identify what I call dangerous successes. So this is where the system behaves as it's designed, and that also leads to a hazard, loss, or an accident. If that makes sense. I hope that answers your question. So yeah, let's move on. So talking about insufficient inlet pressure addresses whether there was necessary pressure from the propellant to reach the thruster. Data demonstrates there was sufficient helium to reach the oxygen tank and sufficient commodity from the oxygen tank to reach the oxygen thruster manifold. Okay, so they're sort of saying that that's not the issue, or they don't believe that's the issue. Leakage, non-helium, explains that the vehicle had too much leakage present for the thrusters to fire correctly. There was no significant pressure differential in the oxidizer manifolds or upstream lines, indicating no gross leakage of commodity. So if we just think about things through this control loop again, if we're talking about leakage of helium, non-helium, then we're sort of talking about this control path here. So the thrust controller opens and closes valves, releases pressure from the various fuel area, fuel storage points. They come together, they mix in the oxidizer manifold, and then that generates the thrust. So they're saying that there's nothing wrong with that control path from what they've identified. So no failures with that so far. Blocked reduced flow branch of the fault tree is broken down further into 131 failed something valve and 132 FOD. So I'm presuming that's foreign object debris. 133 failed thruster valve, so that's a component failure. Then we've got prop filter blockage. Then we've got demand from other thrusters. So demand from other thrusters is interesting because that might imply some issues with the thrust control system, trying to control different thrusters in simultaneously perhaps. Or it could be due to the control path in some way. There might be something going on there that might be failure related or might not be that we need to consider. So the next section breaks that down. So we've got 131, 135. So 131 failed valve investigates how this failure would result in the thruster being unable to receive propellant. There is no indication of a failed something valve such that it was partially open or transient, and the vehicle could not have completed the necessary burns to reach the docking access with this type of failure, and this type of failure had manifested. Just think about that. So there's no indication of a failed valve because it was partially open transient, and the vehicle could not have completed the necessary burns to reach the docking access with this type of failure, and thus type of failure had manifested. Okay, so they're saying that they don't think that failure occurred. There's no indication of it. Okay, but again, it's about failed valves. So if we're talking about failed valves, that's, in our control path, it's an actuator of some description. Who or what controls that valve, and how might there be physical issues with that valve or some other thing going on with that control path that we might want to consider. But again, this is a bit academic because obviously, if I remember correctly, this part of the spacecraft was burnt up on re-entry, so we can't go back and look at it. But I suppose if we have a real one, an Iron Bird test rig, for example, where we can go and look at the thing on the rig, maybe we could explore that a bit further. Right, demand from other thrusters. Let's just check if anyone's chatting me from YouTube. No. What about Facebook? No, nobody on Facebook. Oh well, never mind. So everyone's on LinkedIn. Hello. Fantastic. So demand from other thrusters. That there was insufficient pressure from all of the other thrusters firing at the same time, causing a reduction in flow that may impact one or more thrusters. The doghouse manifold pressure shows full pressure of something was maintained during firings, which means sufficient commodity to provide for all available thrusters. Okay, so again, this is a bit of a combination of thrust controller, and the different control paths, in this case, from the various thrusters and the doghouse manifold and all of that good stuff. Now, the doghouse manifold pressure is a type of feedback. So is that just one source of data, or is it different sensors on the manifold? Is it possible that we could have had an issue with the sensory feedback that is leading us, or should I say the investigators that wrote this report, did the investigation and wrote this report? Is it that perhaps that doghouse manifold pressure is providing misleading information for the investigators? Is that something we want to be mindful of? You know, is the evidence in front of us actually the evidence that we think it is? And is it potentially leading us down an incorrect path of inquiry? Fantastic. So let's move on again. Let's keep going this way. So let's make that big enough so you can read it. Yeah, just interesting in the chat. Let me know. Are you watching this on your iPad or your iPhone or other mobile technologies? Or are you watching it on a computer, on a PC? Or maybe, if you're really cool, have you got it on a big TV screen in your house? And of course, there's always going to be one person, and I hope Kyle's watching. They'll be listening to this on their journey in the car. So if you're listening to this in the car, hello. I'll do my best to describe what's on the screen as best I can. Okay, so B132, FOD, foreign object debris, addresses that significant amounts of FOD may result in a bad mixture ratio, while reduced thruster data consistent with a mixture ratio shift could result from FOD. Other thrusters on manifold did not see performance reduction and or failures. Filter upstream of the manifold ISO protects the relatively small downstream manifold. Any FOD in the manifold should have affected the thruster much earlier compared to the time of failure. Importantly, final hot fire results at the ISS refutes the presence of FOD. Okay. But again, it's indirect evidence. It's, you know, if we're thinking about us as investigators, this is us, the controller of the investigation, and we're getting feedback about the subject of our investigation. Are we receiving feedback that implies this is the case, this is the situation, or is it circumstantial? Bit of a rhetorical question there. Anyway, right. B133, failed thruster valve, is divided into 1331, which is oxygen and helium. The helium portion of the fault tree covers FOD. In the B11321, FOD in helium line, and 13322 something valve failure. The B1331 oxygen branch of the B133 failed thruster valve is divided into main seat separation of the poppet Teflon seat, something poppet fracture, hot valve injector, blank shift, inadequate blank margin. Okay, so then it talks about those topics in further detail. So let's start with the first one. So 13311, main seat separation, extrusion of the Teflon poppet. Now, it would be really nice if there was a diagram that explained what all of these things are, because there's some interesting names, and those names to me as a predominantly aerospace and defence engineer might mean something completely different in this context. So we just have to be mindful of that. So the main seat separation identifies the possibility that the oxidizer poppet, so I'm just going to highlight that as a potential candidate for inclusion in our control structure model. The oxidizer poppet of the thruster valve could extrude, causing a blocked or reduced flow. Blocked or reduced flow means there is insufficient flow of propellant reaching the combustion chamber. Post teardown of the WSTF thruster. WSTF, everybody. Can we remember what that is? WSTF. I'm not sure it's what it sounds like. Where is it? WSTF. Oh, there we go. Acronym. There we go. White Sands Testing Facility. I should have remembered that. It was 2 months ago, though. So the White Sands Test Facility thruster. So I'm presuming that's where they have a test rig of some description at the White Sands Test Facility. And they've examined it, maybe done a teardown of it. Showed significant deformation of the Teflon seal on the oxygen valve poppet. Therefore, the evidence supports this being a contributor to the thruster fail-offs. Okay, interesting. So this is a significant deformation of the Teflon seal on the oxygen valve poppet. So if we just went back to our, I'm going to put a board around this because it's difficult to make out. Let's put a nice board around it. What colour should we use? There we go, a nice big blue border. There we are, I can see now. Right, so if we're thinking about this through the lens of a cast accident analysis, so I'll just zoom out to our cast accident analysis page. Where is it? There we go. So yeah, here we go. Look. So if we're looking at this physical process analysis, because we're talking about physical components in this stage, we're talking about actuators in the thrust control system control loop. What are there any physical failures with this component we need to think about, or is is this poppet supposed to deform? Is it defined? If it is the definition of it such that it's supposed to deform to some extent, or is it an issue with the context within which it's operating? So if we go back and think about the Challenger space shuttle disaster in 1986. The O-ring seals on the solid rocket boosters, they were qualified for a particular temperature range. And for various reasons, the decision was made to launch when those seals were outside of their temperature range. And so, yes, the seals failed, but, we knew they would fail in this case because they were outside their temperature range. So is it that the seals failed? Or is it they were operated outside the temperature range? And why did it make sense for them to operate outside the temperature range? So just be mindful about thinking about physical failures versus the context within which these things are in. Because if they're not supposed to be in that context and then you operate them and then they fail, yes, it's a physical failure, but it's more to do with the context within which they are operated. So I'm trying to get you to think about it through the lens of an investigator and through the lens of cast and how you might think about it in the flow of a cast analysis. Right, where were we? So we were there. There we go. That's where we were. So failed thruster valve. There we go. Yeah, and we went to this bit here. Okay, so therefore the evidence supports this being a contributor to the thruster fail-offs. Okay, so this is about the control path from the thrust controller to the thrust as a control movement of the spacecraft as a control process. So we're sort of focusing on this, on the control path, how the control actions become manifested in the physical world. The next one is about main seat separation, exclusion of the Teflon poppet, and failed thruster valve. So heat, pressure behind the poppet, transitional Teflon swelling, NTO. I can't remember what NTO means. What does NTO mean, everybody? Here we go. NTO, nitrogen tetroxide. There we go. That stuff, yeah, okay. Traditional Teflon swelling, nitrogen tetroxide. Inadequate poppet seat retention. Okay, so I imagine if you had access to the failure modes and effects analysis for this part number for the Teflon poppet and the thruster valve, I'd imagine that looking at that that failure modes and effects analysis, you will have some lines in there, that failure modes in that list that relate to these elements. And if there isn't, there's a gap in your failure modes and effects analysis that needs to be filled in. Now, I don't know, but I presume that the design and manufacturer of this bit of kit, this piece of equipment, they will have somebody, a boffin, a PhD or whoever it is in the organisation that knows absolutely everything about the physics of failure of this thing. And so if what this is highlighting is not within that analysis and that physics of failure expert is not aware of it, I assume that they are, but if they're not, then there's a bit of a control loop there, a design assumptions and a traditional safety analysis loop that we need to make a recommendation for and go and dig in and make sure that failure modes and effects analysis is updated. But also, are there any other components in this subsystem, in the thrust control subsystem, that we may also need to look at and review? Because there could be issues that are specific to this that might have a theme that affects everywhere. So we've got a question there. Someone is so Nick's on his iPhone. Fantastic. Join the iPhone club. Yeah, there we go. And then Nick says, new to this, Simon. I understand what stamp is, but what is cast? Okay, so great question, Nick. So let's jump to some slides up here, shall we? Where can we start? There we go. So I need to update this slide, so I apologise. I should have done it earlier. But let's just assume that it's updated. No, why is it not working? Come on. Anyway, right, there we go. That's the slide that needs to be updated. So, okay, so STAMP is the ideas and principles and the foundation. The prime concept in STAMP is about control structures and control loops, and that accidents are not just due to failures, they're due to inadequate control. And so the way to prevent accidents is to enforce safety constraints on our system and how it's designed, how it's operated. And the way we do that is through a control structure. Now, what CAST is the retroactive reactive analysis to an event or an accident, or if you're doing an investigation, a safety investigation, you will use CAST to essentially uncover what was the control structure involved in your accident and how did that contribute to the accident itself. And the way it does that is very similar to STPA in that you have a foundation phase where you define the losses that have occurred. So in this case, after an accident, you know what's happened. You're not postulating. You define the specific hazards or capture the specific hazards that are relevant to your investigation. So in this particular Boeing Starliner, we're talking about issues and hazards associated with thrust control, trajectory control, path control of the spacecraft. And then, of course, the high-level safety constraints. So logically, what are the high-level safety constraints that we would like to have had to either eliminate or control these hazards, or if they do occur because we've not controlled them properly, how do we respond and recover from them? So that's what these are. And then these essentially help to define and capture, well, what is the control structure that is involved in this particular accident, and how does that control structure not enforce these high-level safety constraints? So in this case, we had inadequate thrust, or thrust control was inadequate in various different ways. So what is it about the design control structure, the operations control structure, that actually contributed to that? And of course, STPA hazard analysis looks at the very broad big picture of all the possible unsafe control actions and causal scenarios that lead to an accident, whereas CAST is very focused on those specific controllers and control actions that contributed to this particular accident. And of course, as you're going through the investigation for this accident, you may well find weaknesses in your design, in your control structure, for other accidents that haven't happened yet. So you have to be prepared that you might get some bonus causes of accidents that haven't happened yet. But as I say, CAST is very much focused on the specific event itself, and it can help you understand what were the physical aspects, so what are the physical issues, the failures that contributed to the accident, what are the control actions that contributed, and of course, how did the structure itself, how did the control structure and how it fits together and interacts across different hierarchical levels, how do they contribute to an accident? So this is the physical process analysis. So this is where we look at the control process. We talked about actuators and sensors. Are there any physical failures that we need to think about? In this particular case study, it's evident that there are some physical failures that contributed to this. And so, of course, if they're physical failures that we didn't anticipate, that suggests that there is an issue with the design, test and qualification of that equipment, that system, that component. So what is it about that control structure, the design, operations and test control structure, that missed this? I mean, it may be that they did do some tests, they have a test rig, they did some tests on this and they maybe found some issues, but somebody in the engineering organisation decided, actually, for whatever reasons that made sense to them at the time, without hindsight, knowing this accident has occurred, why would it make sense for them to say, yeah, let's go ahead, let's risk it? Because there may be a genuine reason why they decided. They may have known that this was an issue, and the organisation has decided, well, we're going to take the risk, we're going to live with it, and then boom, we have an incident. So, we shouldn't be pointing fingers and blaming people. We should be trying to understand why would it make sense for them to make this decision. But of course, there is always the potential that somebody has, made some potentially reckless decisions, and you've got to be open to that possibility. But the prime objective of a safety investigation shouldn't be to try and point fingers and blame people. Oh, it's their fault, it's human error, whatever it is. We've got to be more humble than that, because if we go down that path, we potentially don't get, we don't learn enough, we don't go far enough to be able to prevent this in the future. And then in terms of component analysis, so we'll be looking at the control structure, looking at each of these controllers in that structure to try and understand, what are their safety-related roles and responsibilities and safety requirements, constraints related to that specific controller, whether it's a human or an automated controller. Then we think about, well, what is the control and feedback ability of that controller? What control actions and feedback can it provide, should it provide, does it get? And then how are they actually implemented? What actuators and sensors are involved? And is it direct control or is it remote? Because if you think about a ground controller, they're not on board the spacecraft. They are essentially communicating it remotely. And of course, the further that spacecraft is away, the bigger that feedback gap is, the time lag is between providing control actions and getting feedback. So there's possibly there will be an automated controller, a computer system on board that is between the human and the spacecraft, the control process. Then we think about, what are the contributory control actions of this controller? In the case of this thrust control, is it just purely mechanical failures involved in this, or is there something that the controller is doing or not doing when it should be doing it that we need to think about? And then we think about, what are the, we capture, what are the reasons, why is that, how is that, what are the reasons and explanations for that? Are there any issues with actions, behaviours and decision making? Were there any issues with mental models or process models and beliefs? So did the controller believe that it was controlling things correctly, and the reason they did that is because they had issues with their process model, their beliefs? Is there any context that we need to be mindful of, any other contextual factors? And then in the case of the structure itself, so this is, how does the overall control structure contribute to this? There are 7 sort of broad topics that are listed here and in the literature. But you might have many more specific topics in your experience in your organisation. So communication and coordination. Are there any issues between the control process and the controller, or maybe across different organisations? Maybe there is some design organisations that need to communicate with their suppliers, and for whatever reason that's dysfunctional and contributes to poor decision making. Are there any issues with structures and architectures and interactions in the structure itself? Are there any dynamics and changes or evolution of that structure? Product, service or system itself, the environment, the organisation and humans themselves, including human behaviour, perhaps even complacency or perception. The classic one with perception is, there's a probability of x to the minus y to the minus 10 or 11 or some ridiculously small made up number. Oh, well, it's obviously safe then because the number's so small. And so they convince themselves, it's a small number, so don't worry about it. Whereas they've overlooked the potential for dangerous successes that are not related to failures. Then there is the safety management system. Is there any contributions from that? The safety information system, the SIS. And I know this sounds really formal, but a safety information system could be as simple as somebody sending an email with some technical data in it to somebody else, and that's somebody else not seeing the email or copying and pasting the information wrong, and so it propagates throughout the control structure. Everyone's favourite, safety culture. So if you've got safety people doing important safety reviews, and for whatever reason the program timeline takes precedence and safety issues are kicked down the street into the future, then those issues are not managed carefully and then dealt with later on, that can undermine safety culture. And then, of course, everyone's other favourites, economic and environmental aspects. So whether that's external or internal to this particular loop or the broader structures, or whether there's any physical or non-physical aspects that need to be thought about. And of course, there's a mention here about temperatures and heat dissipation. So that could affect, a particular loop, but it could also have an impact across different areas of the control structure. So in a nutshell, that's a very quick nutshell, that's what CAST is. And of course, CAST is an acronym itself. So in your question there, let's just put that on the screen. What does CAST stand for? It stands for causal analysis based on systems theory, or depending on if you're looking at other literature, it might say that it's called causal analysis based on STAMP. And in a nutshell, it's just a safety investigation method or safety analysis, accident analysis method. So after the fact, so it helps to avoid what do we call it? Hindsight bias. But of course, trying to manage hindsight bias is a challenge in its own right. So we've got someone else asking a question. There we go, Thomas. A traditional RCA wouldn't answer why they were operated outside the operation limits. The background of the decision to operate it regardless, the physics of failure would be quite obvious. Yeah, fantastic. Great observation there. So thumbs up. Thanks, Nick. So yeah, let's move forwards then. So we talked about that. Let's go back to where we were. Right then, so let's have a look. Where were we talking? So therefore, the evidence supports this being a contributor to the thruster fail-offs. So this is about the Teflon poppet. So what I would do is, if this is the, let's think about the Teflon poppet for a minute, and let's do a mini cast. So if the Teflon poppet design is the control process, we have the Teflon poppet designer, tester and qualifier as the controller. So what is it that they do about the design, and what feedback do they receive about that design, that implementation, to make sure that it's behaving appropriately? And if it's not behaving appropriately, how do they make decisions to accept them, to move forward with the program, whatever that is? So this will be, if we had a team of people involved in this investigation, I would allocate, if I was the team leader, the lead investigator, I would take that particular topic and I would give it to somebody to go off and do a mini cast, about that particular context, so that we understand who or what is involved in that, what control actions and feedback they had available to them, and why would it make sense for the design to be the way it is. And that, just by doing that one little mini investigation, you'll probably find some really interesting things to think about and perhaps some really powerful recommendations. Okay, so where are we now? Let's talk about main seat separation of the failed thruster valve is divided into heat, pressure, traditional Teflon swelling due to the nitrogen tetroxide, inadequate poppet seat retention. So heat identifies that excessive heating could cause the poppet to extrude, reducing flow. Poppet extrusion was observed in the post-test teardown of the White Sands test facility thruster unit. The initial heating caused by the internal doghouse temperatures addressed later in C41, and the follow-on heating induced by B133142 RCS thermal soakback then caused excessive temperatures beyond the capability of the thruster soft goods, causing the Teflon poppet to extrude. The evidence supports this being a contributor to the thruster fail-offs. Okay, so if we're thinking about this control loop, this control path from the thrust controller to the actual, trajectory of the spacecraft. Inside this control path, there are obviously some environmental questions involved in that. Now the question also raises, well, why is it designed that way? If there is a question over the temperatures, the environment of these actuators, then why would it make sense not to provide cooling or some kind of other environmental control? Did they have environmental control? Was it necessary? Was it identified as necessary? If it wasn't, then there's a question there over the design. How did the design get its way into space without having that that thermal control considered? And of course, I'm not trying to speculate or point fingers or anything. I'm just trying to help you appreciate how you might want to progress your investigation, what paths, what questions you might want to dedicate some energy and time and treasure to looking at. Okay, so yeah, okay. So pressure behind the poppet. So this is about heat. This is about pressure. So pressure behind the poppet identifies the possibility that nitrogen tetroxide could seep behind the poppet seal. Why is that moved? I think I must have done it accidentally. Nitrogen tetroxide could seep behind the poppet seal, and that the trapped fluid could produce an upward force on the poppet seal when heated. This upward force upon the poppet would generate a void, allowing additional NTO to ingress behind the poppet, thus repeating the process. This process likely requires excessive heating. The mechanism for this is not fully understood, and there may be other elements that impact the generation of this void. This void was identified via CT scan of the post teardown of the White Sands Test Facility thruster unit. The evidence supports this being a contributor to the thruster fail-off. Interesting. So it could be one of, or both of those perhaps, contributing together. But again, we're still focusing on the control path. We're still focusing on the physical items themselves. B133113, traditional Teflon swelling nitrogen tetroxide, identifies the possibility that NTO causes the Teflon to swell and impede the propellant from reaching the chamber. Teflon poppet swelling due to NTO exposure was observed during the WSTF testing. The growth of or swelling of Teflon when exposed to NTO is between 8 and 9%. It is unlikely that this effect alone generated the observed failures. The thruster is designed with a poppet stroke to account for this swelling. This effect did likely have an impact on an extruded Teflon poppet, allowing the volume of the poppet to expand slightly more. The evidence supports this being a contributor to the thruster fail-offs. Okay, so this part of the control path in this control loop has been designed with this in mind, so they were aware of it. The mental model of the designer is NTO exposure leads to growth or swelling of the Teflon, and it's between 8 or 9%. And they've designed it so that they can tolerate that. But the heating effects that are mentioned earlier on, or the gap due to pressure, may not have been considered as part of the design. So as an investigator, I'd go and ask questions of the designer and look at the design information and say, well, look, have these things been considered given the evidence from the test rig? Now, of course, there's a broader question of, well, hang on, if they found these things post-accident on the test rig, did they find these things on the test rig prior to that point? Or is it only now in the aftermath that they're doing this test? And if so, why was this test not scheduled earlier before they put some people on board this spacecraft? And again, this is from a control loop perspective, I'm clicking on the wrong thing. If this is the program, this is the project, and the decision by leadership is to, let's go to space, everybody. Why would it make sense for them to accept that? If they've not done the testing and got the feedback that they need, then they shouldn't be making those decisions. The control structure should be designed to prevent them taking action and launching this thing with people on board if that testing has not been completed. So what optimization, what has a project manager done? What has a test manager done? Are there any minutes of meeting where they've been, fighting with each other? Has that actually taken place, or did they just miss it? And if they missed it, there's an immediate recommendation there for future flights. But of course, let's not point fingers here. Let's understand what happened and why it made sense, and let's make appropriate recommendations for the future. Bearing in mind that some safety constraints are absolutely necessary and cannot be undermined, and there are others that maybe people are willing to take the risk on, and maybe in this case they just took the risk on the wrong racehorse, so to speak. Okay, so inadequate poppet seat retention. So this is B133111. Inadequate poppet seat retention identifies the possibility of the design of the poppet being insufficient to prevent the Teflon seal from extruding, moving outward, thus reducing the flow of propellant. The inadequate seat retention is a failure caused by inadequate engagement of the thruster valve poppet swage. So this is another bit of kit. It'd be nice to have a picture, but I can understand why it might not. So there's the poppet. Then there's the Teflon seal. Thruster valve poppet swage, which can also create a leak path to the back side of the poppet. Swage refers to the metal on the sides of the poppet that help to keep it in place. If there was more defined swage, this may have prevented some of the observed extrusion. So again, from a design perspective, if that's the physical arrangement, why was it designed that way? Why did it make sense to design it that way? Again, did they know it was a problem? Maybe it was concessed. Maybe it's an issue they knew and concessed it, and everyone thought, well, the likelihood of this being a problem in flight is 1 to the minus blah, so it's not a big issue. But actually it's happened. Okay, so as a comparison, Moog, I believe Moog is a company. In fact, is it in the acronyms list? M-O-O-G. No, it's not. So we don't. I'm assuming that's Moog, the Moog that makes flight control systems and things. I'm not sure. Found a similar issue during ATP of the hardware. So ATP is Acceptance Test Procedure. ATP. So Acceptance Test Procedure of hardware bound for the Japanese Experimental Hope X project in 2000s. This hardware was identical to the hardware used in the shuttle APU upgrade, leading to a presentation regarding the issue presented in STS 101 Flight Readiness Review, I'm presuming. FRR, everybody. Yes, it is. Look at that. I remembered an acronym. Fantastic. That's the thing working in multi-domains. You have all these acronyms floating around in your brain, and sometimes you have to repeat them and it pushes one out the other side. There we go. Right, so the Flight Readiness Review for STS 101 showcasing separation between the concerned... So STS 101, if you don't know, is the Space Transportation System Flight 101. I think that's correct. Anyone from NASA that's watching this, please give me some abuse in the comments or confirm that that is correct. STS 1... Because I'm a bit scared of doing live Google searches on live streams in case something really dodgy comes up, because you never know. There we go. So STS 101, I believe, is Space Transportation System Mission 101 Flight Readiness Review. So before they go flying, showcasing separation between the concerned hardware and the hardware set to fly. In this instance, during an ATPS test campaign at the manufacturer, poppet extrusion was noted after the poppet seat had only been exposed to water. Not NTO at ambient temperatures, not elevated temperatures. So they did a test. Poppet extrusion was noted. So the manufacturer's mental model, so if we go back to our little control loop here, the manufacturer did a test, and that test showed them that poppet extrusion was noted. So they noted it down. After the poppet seat had only been exposed to water. So this test was with water. It wasn't representative of the operational situation. And at ambient temperatures. So again, it's not representative. Teflon poppet seats of this geometry can demonstrate extrusion without propellant or high temperature exposure. Okay, so it sounds like this design is interesting. I'm not an engineer with experience on the design of this thing, so I can't give a sort of technical opinion on it. But it's just interesting that they're aware that that's a potential issue. So how was that issue escalated throughout the control structure? So we've got a mention of Moog, we've got a mention of the Japanese space agency, Japanese missions. So there's Japanese engineers involved in that, lots of stakeholders. They'll have in fact, sorry, I'm just going off on a bit of a tangent here. So let me just go to this cast bit. So from a structure analysis, a controller, in this case the manufacturer, they had a mental model of belief that there was an issue, potential issue with the poppets in ambient temperature water. And they've identified that potential issue. So how does that issue get communicated around the control structure to the various stakeholders? This is the safety information system I was talking about. So if there's an issue, how does it find its way around the control structure to the various stakeholders that need to know it. Is that something we need to go and investigate? Has there been an issue with the safety information system? Because if they knew about it and that wasn't communicated, then that is something we need to nail down. Because there could be other issues that have also not adequately found their way around the control structure that we haven't even thought about yet. And again, I'm not. One of the questions I'm always asked is, well, where do we stop, Simon? It sounds like we're going to analyze the entire universe, and that's not what I'm trying to suggest here. What I'm saying is this method allows you to choose where you want to spend your energy, time, and treasure. You don't have to boil the entire ocean. You have to be strategic. And that is a challenge. That comes with experience. And I can't possibly suggest to you how you want to conduct your investigation. But this method allows you to start exploring those questions and then assessing whether you want to spend your time, treasure, and energy exploring them. But I think in this case, they've said that this is potentially one of the causes. So I'd suggest maybe we should go and have a look at that in a bit more detail. What is it about this poppet extrusion and the physics of the physics of it that we need to think about, and how is that information communicated around the control structure? Because it's probably documented somewhere. There's probably a memo or a note somewhere deep in someone's email or the PDFs that say this is what the issue is, and it's just not find its way to the right decision makers. I am anticipating that. I've seen that a few times over the years. Anyway, Teflon poppet seats of this geometry can demonstrate extrusion without propellant or high temperature exposure. So there's a question there. Teflon poppet seats of this geometry. Well, are there any other geometries that were considered? Was there a design review that said, well, we've got a selection of geometries and these ones do this, what we're talking about here, and these other geometries don't do this. So why would it make sense to go with this geometry, presuming that's happened? Is it a design change? Is it on an action list that's been there for many years and nobody's actually followed up and got it nailed down? Okay, another notable difference is that this comparison hardware utilizes teeth to keep the poppet in place, unlike the Starliner valve. Okay, so this is a different design. So this is... So the hardware was identical to the hardware used in the shuttle APU upgrade. Right, okay, so I'm guessing then that whoever's involved in the investigation knew all about the shuttle stuff, the shuttle upgrade, APU upgrade, and the history of it. And then they've highlighted that, well, actually that design, the shuttle design, the Japanese HOPE project, they used teeth to overcome this problem. But the Starliner valve doesn't have that. So there's a question there over two things. The first is the corporate knowledge, so to speak, of these kind of issues and how that is used to enrich future projects. Because that learning has been done for the space shuttle and the HOPE project. But why was that learning not found its way into this particular design? And is that because this design is from a commercial provider? It's not come from NASA themselves when they've done, when they were involved in the design of previous projects at a much higher level of detail. And are there any other potential issues that NASA has got documented that should be fed into the crew commercial program? Now, from a safety perspective, of course they should do that. But from a commercial perspective and a intellectual property perspective, there are some potential tensions between doing what's right for safety and what's appropriate from a commercial perspective. Because NASA might have a lot of technical experience and know-how that would, save a lot of money and dollars for the commercial organisation that's building the spacecraft, but surely there should be some reciprocation of that value, provision of that value. And how do we deal with that? I'll leave that with you. That's a rhetorical thing to think about. The finding here was that the teeth had been filed down too far during the deburring process, allowing an improper engagement of the Teflon to remain in position. Right, so there were some teeth, but for some reason they were filed down too far. Right, here we go then. So, interesting. So if this is the manufacturer, the person or machine, maybe it's a robot, maybe it's a robotic system that's doing the filing, And that's done a deburring process. So that's what these control actions are. Do a deburring process to this particular process, which is manufacture of the Starliner valves. And they've been filed down too far. So that is control action too long, perhaps. So the provide deburring action to component duration too long, or and the context is when there is a deburring limit that needs to be maintained. So there's a question there over the machinery, perhaps the people that are involved in that, and also the inspection and quality. Because if this is identified as a flight critical part, you're not going to get adequate thrust if this is not burred properly. Then is there any feedback to that check to make sure that it's been done properly? And is there any independent feedback path to make sure that it's been done properly and it can be qualified and certified? So again, this is a mini investigation in its own right of how this thing was manufactured. I hope that makes sense. Give us some abuse in the comments if that makes sense, because I'm sort of going down a lot of different pathways there, and I'm really trying to stretch your imagination as to some of the topics that you could explore and how far you could go if you chose to use this method. Okay, so whilst there is hang on, I need to zoom in again so you can see. There we go. While this is not a one-for-one hardware comparison, this corollary it's been a long day. This corollary, easy for me to say, corollary representation shows that extrusion can happen without adequate poppet seat retention. Okay, so I think the emphasis there is about poppet seat retention. It's about control of that poppet and how it moves. And it sounds like the design of this particular one and the way it's been manufactured might be an issue. So the question is, for the design and manufacture of this thing and the test of it, what does that control structure look like? And how did that control structure design something that's potentially prone to this issue? How was it manufactured so that it's prone to this issue? And then what was the test and qualification of it? And how was it signed off? And of course, you might, if you want to go really far, you could say, well, hang on, has there been any previous instances of this on the same spacecraft, different manufacturer, different program, and how was that actually fed back into, or not, fed back into the design of this one and the acceptance of this one? Fantastic. Right, let's keep going. So 1, 2, 3. Let's just have a quick zoom out, see where we are and how far we've got to go. So we've still got quite a way to go through this report, but we're making good progress. I hope what I've been saying makes sense and that it's given you some food for thought. Of course, if you do, if you're trying to do this and you want some help, please reach out, send me a message or visit my website and we can have a conversation, because I'd rather spend, half an hour talking to you on the Zoom or, answering any questions that then give you, move you forwards. I'd rather you didn't sort of stand for 6 months banging your head against the wall on something that I can answer in a short amount of time. I'm here to help and support. Okay, so B13312, damage slip. So this covers that the blank, whatever that is, to move the poppet on the oxygen fuel lines could become damaged or disconnected, slipped, leading to the valve not properly operating in opening the fuel oxidizer poppets properly to allow sufficient flow into the RCS. It's not radar cross-section, it's reaction control system. So remember that one. Thruster combustion chamber. So I'm just going to highlight this while I think about it. There we go. So this is to move the poppets on the oxygen fuel lines could become damaged or disconnected, leading to the valve not properly operating in opening the fuel oxidizer poppets properly. So this blank, whatever this blank is, that is a type of controller in some shape or form. Or we might choose to treat it as an abstract part of the control path where these control actions are provided. But if we were doing a cast together, doing a stamp analysis together, I'd recommend we dig into that and understand, well, what is this component? You know, if it's supposed to move the poppets, and it could be damaged or disconnected, leading to the valve not properly operating. Clearly, that is an important topic we need to think about. So let's see what the rest says. This would result in either diminished or no thrust. Damage, some blank damage slip would be evident in the available data, as the thruster valve would be unable to adequately move. There would be no flow to the combustion chamber, and significant damage would likely result in gross leakage. These effects were not observed. So again, if we think about this loop, this jigsaw piece, through the lens of investigator, so the investigator's making decisions and asserting claims about this thing, this blank, and that damage or slip associated with it, effects of that were not observed. So the question is the feedback that the investigator getting actually adequate to be able to back that statement up? I don't know is the answer. I like the other elements, the poppet stuff, I'd anticipate that this should be captured by a rig test of some description. There should be a test program that identifies this or not. The failure modes and effects analysis for this component, I'd argue going and looking at that, having a review of it, that should contain some lines related to it. If it doesn't, then the FMEA needs to be updated. So moving forwards, poppet fracture identifies that damage to the poppet from firing the thruster causes blocked, reduced flow. Poppet fracture would be permanent and could produce very low thrust level, as seen repeatedly on B1A3. So that is one of the thrusters, B1A3. Following reselection post fail off. Poppet fracture, similarly to blank, would likely result in gross leakage of commodity out of the thruster valve. There was no indication of gross leakage of commodity. So that's sort of saying two things. One is that poppet fracture could contribute, and it may be related to B1A3, but we can't get evidence to prove that or not. But if it did happen, it would likely result in gross leakage, and there's no indication of that. So again, if they're identifying poppet fracture as an issue, is that actually addressed in the safety analysis already, or is there a recommendation there to go and consider the potential for poppet fracture and how to eliminate it from the design or live with it should it ever occur? And it sounds like this architecture would not be, if you did have a genuine poppet fracture, for whatever reason. I mean, you know, I don't know, let's say during launch the spacecraft gets rattled around so much that the poppets, you know, there's a common mode that affects all the poppets and they fracture. And then when you come to use them for the first time, they all cause a problem and leak all of your commodity out. Okay, so B13314 hot valve injector identifies that the possibility that the propellants, especially nitrogen tetroxide, in the thruster valve and or injector were heated significantly to the point of boiling. Okay. This reduces the flow into the RCS thruster combustion chamber, leading to diminished combustion and reduced thrust. Excessive heat could cause injector warping, which would cause loss of performance by reducing optimal propellant mixing. However, this would not maintain the level of thrust observed in B1A3. The closest available temperature sensor, there we go everybody, temperature sensor. So let's just go back to our little loop, everybody. So we've got a temperature sensor that provides feedback to some controller. It's not really clear which one it is. Indicated an initial valve temperature of blank and flight valve temperatures at time of post-release selection firings were reading below the boiling temperature of NTO. Both initial temperatures and post-reselection temperatures of the valve are based on Therm 11A thermal model. So thermal, yeah, okay. So why is it not working? There we go. The Therm 11A model is a simplified model and does not accurately nor adequately correlate the potential effects of the surrounding temperatures. There is an undefined gradient between the PC tube temperature and thermal sensors based on available thruster verification data that is not incorporated into the modelling. It is possible that the valve and the associated soft goods of the thruster valve reached higher temperatures than the closest thermal sensor read. The evidence supports this being a contributor to the thruster fail-offs. Okay, so there's sort of a couple of things there. The first is about the qualification of the valves and understanding what type of heat these things are going to be exposed to, and whether they are designed to withstand that or, live with it. Then there is a question over the sensor architecture and how that sensor information is fed back to a controller. It doesn't really give clarity on what controller we're talking about. Is it the thruster? Is the thruster supposed to receive temperature data, and if it receives at high temperature, it's supposed to cut the thrust off, let it cool down, and then respawn later on? I'd argue if that is the case, let's just have a look at our little control loop here, our jigsaw piece. If our thrust control system is receiving temperature sensor information that is either not indicating that there is a high temperature present when there is a high temperature, that might explain why it doesn't do certain things. Or conversely, if it is receiving genuine temperature information that it shows high temperature, why is it behaving the way it is? Why is it providing the control actions that it is? Now, of course, I haven't really got much to go on here. So, of course, if you're involved in this kind of stuff and you know the detail behind what's written here, I'd suggest just having a think about it through that lens. These temperature sensors, how are they actually involved in this control loop? Are those temperature sensors even involved in that control loop for thrust? Because it may be those sensors just go to another computer for information to be downlinked to Earth. It's not actually involved in the control loop for thrust, or maybe it is. I don't know. If it's not, maybe it needs to be. Maybe there's a question there over the design architecture of the thrust control system. And then this thing called a Therm 11A thermal model. I don't know what it means, the context of that model. Is it a model? Is it a process model or a control algorithm that the thermal control system or the thrust control system uses to make decisions about control actions? Or is it a thermal model that the designers, the operators use to understand the physics of their design and how it's supposed to behave? So it could be a design issue, or it could be a question for testing. Are they testing something that's representative, or are there limitations in the way that they test and the beliefs that they have because of the limitations of their model that the test team, the designer, has accepted a design based on a limited model that has contributed to this situation? I hope that makes sense, because it's quite... I'm sort of really stretching your minds there. There we go. So let's have a look. So yeah, that would be a mini project to go and have a think about and explore, I think. The effects of heating upon propellants are captured in B141 two-phase flow and subnodes 1411 vaporization and 1412 cavitation. Pardon me, the heating caused by the reaction control system thruster firings is captured in B133142 RCS thermal soakback, and the potential effects, external effects, and the potential effects, external effects. I think there's an extra word in there, so if you want to edit that out. Such as thermal, is captured in the thermal sections of the C failure from the environment. Okay, let's keep going. So we've got B133142 RCS thermal soakback identifies the possibility that the structure of the RCS thruster retains heat, and the heat is unable to be dissipated from the firings of the thrusters, causing the propellants to heat rapidly. Heat soakback for this node is defined as the heating from the thrust chamber. This heating is strongly dependent upon A3122 pulse train, duty cycle, pulse width, duration. Due to insufficient qualification testing that does not adequately inform the associated RCS thermal model, it is not possible to fully quantify the effects of A3122 pulse train, duty cycle, pulse width, duration on the thruster. The evidence supports this being a contributor to the thruster fail-offs. Interesting. Okay, so there's sort of two broad topics there. One is about the design and how it responds to thermal soakback and the generation of it and all of that good stuff. So that's the first thing. The related topic to that is, given we recognise there's a hazard associated with thermal soakback and how it affects propulsion, has that hazard already been identified in the safety case, the safety assessment? I'd argue it probably has, but it may not have been explored in the deep level of detail that's necessary to really flesh this out. The second topic is about the thermal environmental control system function, or whatever they describe it as in their design. Does that thermal control system, environmental control system, does that have a contribution, a link to the thrust control system? Are they linked to each other in some shape or form? Because if they know that thermal soakback is an issue, I'd argue that there's a question there over the thermal control system design. Is it designed to deal with this and remove that heat or manage it accordingly? And it's not just heat, it could also be cold. It might need warming up, depending on the design and the qualification, the envelope of the spacecraft. And then the third aspect is this question here about insufficient qualification testing that does not adequately inform the associated RCS thermal model. So if we just use our little jigsaw piece again, so if this is the qualification tester and this is the thermal design qualification testing, what feedback do they receive about that testing? How does that update their mental model, their process models? If the RCS thermal model itself is like a combination of process model and control algorithm related to the thermal performance of the spacecraft. So if that model is incorrect, then who controls that model? Who makes sure that that model is up to date and kept up to date? So again, I think that is sort of a related little mini investigation that needs to be considered. It's all related because it's about, if we think back to the spacecraft, if this is the thrust control system and it's trying to provide control actions related to thrust that's not working, what is it about this control path that's causing the problem? Who or what controllers are involved in that control path? Designers, operators, investigators, testers, all of that good stuff. So yeah, also got some people talking. Let's have a look. Who's chatting away? So we've got Nick. Hi Nick, good to see you again. Thank you, Simon. I'm very pleased I made this session as I missed a previously planned one. Got to go now due to other commitments, but thanks ever so much for your detail. You're most welcome, Nick. It's great to see you. As I say, if you do need some help and support, I'm only a phone call away. Take care, and we'll see you around. Thanks for coming along. We'll see you on the next one. Fantastic. So B13315, somehow a blank somehow shifted in place, blocking or restricting the propellant flow into the reaction control system thruster combustion chamber, would result in a permanent PC pressure drop and observable in telemetry. However, there was no indication of permanent change in PC pressure. Okay, I mean that sounds like we're talking about something going on in the control path, but it's not really clear what that is. So we'd need to go and have a look at that a bit further, I think. And it says there's no indication of permanent change in the PC pressure. So if this is the investigation team and they're receiving feedback about the spacecraft, in this case, which is the telemetry, is the telemetry adequate enough for them to be able to justify that claim, that decision? We're not sure. We don't know. B13316 blank something something margin identifies the possibility that the blank margin within the RCS thruster blank valve is insufficient. Therefore, the blank valve did not properly operate and blank 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 poppets open properly to allow sufficient flow into the RCS thruster combustion chamber. There are long duration thruster firings indicating the valves were staying open for the full duration. They were commanded open. There is no evidence of the pilot valves not opening, closing properly. So I'm presuming that pilot valves or pilot valves, I'm assuming that's what these blanks are, and they've just not unblanked that. So please just pretend that's blanked and that we don't know what that is. But whatever it is not opening, closing properly. And there's no evidence of that. But that doesn't mean that that's not what's happened. It's just there's no evidence of that. B13321 FOD FOD in the helium line addresses the FOD. That FOD could cause the pilot valve to be unable to move, preventing the thruster valve from moving. There is no data demonstrating blockage of the helium commodity. Firing commands. So you know what it's saying about control actions. Firing commands, they are control actions. So let's just highlight that there. Firing commands. And what we'll do is we'll steal a nice little grey box over there. We'll put it over here. There we go. So firing commands, so control actions, firing commands. So they say that there is no data demonstrating blockage of the helium commodity, and then it says firing commands show the valve opening and releasing flow for all the thrusters except for B1A3. B1A3, the injector temperatures dropped, demonstrating the valve was opening and there was no blockage to the helium line. So when we're talking about firing commands, we're talking about the control actions here, the control path. But it says that firing commands show the valve opening and releasing flow for all the thrusters. So how is the investigator knowing that these firing commands have been provided? Because it may be, there is a scenario, and please bear with me a minute, if we're thinking about all possible logical scenarios for these unsafe control actions, it may be that the controller provided the firing commands and we have some level of feedback from somewhere independent of the controller that says, yes, these control actions have been provided. Or it could be that the controller is saying that it's providing control actions when it's actually not, but what the investigator's seeing is the report that the controller is providing these controls. So it's saying it's doing something when actually it's not. Or it could be that the controller's not doing anything and there's something going on in the control path that appears as if the controller has provided these firing commands. And that there is another scenario where the control process behaves as though these firing commands have been provided. But I'm not sure whether this particular scenario is related to that situation, if that makes sense. And so the question I have is, you know, what feedback does the investigator have that shows whether these firing commands have actually been provided and received? Is it from the control process, or is it from the controller itself, or is it from some other separate censoring, some other separate sensory feedback, if that makes sense? Okay, so the B1A3 thruster is unique in its failure signature, which is consistent with a total blockage of one of the commodities. Oops, a daisy. So that's interesting. So this might suggest that there is a few different causal scenarios going on. And so the issues that we've observed, or that we have evidence for, points at maybe a couple of different issues going on here that may or may not be directly related. You know, one instance could be due to FOD or temperature. Another could do with how the thrust control system is behaving. So what I'm saying is, when you're doing these investigations, always be open to the fact that what you're looking at might be two sides of the same coin, or they might be completely different coins that you're looking at. So don't just assume or presume. They could just be instances of different unrelated scenarios, or they could be directly related. So just be open to that possibility. However, blockage would have to be sudden since thruster performance was nominal during last pulse before failure, as B1A3 was unable to be recovered, and on-orbit data suggests, so this is the feedback on-orbit data that way to the investigators, suggests a complete blockage of the commodity. There is therefore insufficient data to definitively state that there was no blockage of the upstream thruster valve for B1A3 thruster, as its failure signature was vastly different from the remaining thrusters. You see this concept of a failure. I'm gonna go off on one a minute. Just bear with me a second. Failure signature. In fact, you know what? I'm going to use my really cool electric pencil. Let me see if this works, everybody. Oh, look, it's working. Wait. Right, let's see how bad my handwriting is. Here we go. Failure. Oh my God, it's difficult. This is not as nice as writing with an iPad Apple Pencil. Right. Failure signature. Right, the reason I've just scribbled that down is because this term is a bit insidious. And what I mean by that is if you're an investigator and you're using language like this, failure signature, failure mode, all of that good stuff, it's subconsciously undermining your ability to think creatively and be open to the possibility that there might be something going on here that's not a failure. It's behaving as designed, and that is what the problem is. Because if you're looking for failures, then you're going to find failures. And what we're trying to do here is we're looking for failures, but we're also looking for the potential for dangerous successes. And so where it's saying, where is it? There is therefore insufficient data to definitively state that there was no blockage of the upstream thruster valve for B1A3, as its failure signature was vastly different from the remaining thrusters. There could be other reasons. There could be dangerous success signatures if we want to be facetious. There could be other things going on, other signatures of things that are going on. And this is why in STAMP, STPA and CAST, we talk about control actions, we talk about unsafe or contributory control actions, but we also talk about causal scenarios. And causal scenarios are all the different ways that the control loop can contribute to that unsafe or contributory control action. And that group of things, whether it's related to the control process, the control path, the actuators, the controller itself, whether it's to do with the control algorithm, the decision making of that controller, or whether it's related to its beliefs, its process model, its mental model if it's a human, or whether it's related to the feedback path and other information from other levels in the hierarchy. Those four elements of control of causal scenarios, any combination of those could be due to failures or dangerous success. And so we have to be open to that possibility. And using terms like failure signature, I like the term, but it's potentially misleading. It's potentially blinding to those non-failure cases that we need to be thinking about. I hope that makes sense. I'll just get off my hobby horse. There we go. Right. Here we go. So solely for B1A3, there's this delineated on the fault tree, which is reflected in the colour of the associated causes of B132 FOD and B134 prop filter blockage being labelled as unlikely. It is unlikely that the B1A3 thruster had an entirely different failure mode from the other thrusters. So I'm going to get on my other hobby horse. Why are we talking about likelihood here? We're talking about the possibilities, not necessarily then saying, well, it's unlikely or it's likely or not. It's a case of, well, what are the possibilities? And let's seriously consider those possibilities and then let's decide whether we need to do some work to eliminate them or respond to them or not. Not just say whether they're likely or unlikely and then forget about it. There is a potential loss of learning there. But I understand why the investigators have done it this way. I'm not trying to belittle them or anything like that. I'm just saying we need to have less emphasis on whether something is judged to be likely or not. Because going back to this, if we're the investigators and if we're providing control actions which are questions to go and ask as part of the investigation and conclusions, we need to be mindful that our biases, our beliefs, our decision making could be undermined, such that we're focusing on failures and likelihood, and actually there's other more important stuff going on that we're just not privy to because we're not focusing on them. We're distracted by likelihood assessments. Anyway, I'll get off that horse now. Here we go. Right, so B13322 blank addresses that the blank valve becoming stuck and causing the blank to not move, thus causing the thruster valve to not open, similar to B13316 inadequate blankety blank, that all thrusters with the exception of B1A3 being capable of firing before and after the event, demonstrating the blank valve is capable of opening and closing properly. This has been deemed not credible. Again, whether something's deemed not credible or not, it just leaves me cold. Because we're just saying, well, there's a possible causal scenario there, but we think based on our experience and likelihood that it's not credible, so we're going to draw a line and forget about it. It's like, well, really, you should be looking at this control loop. Where does that causal scenario fit, and what evidence what evidence do we have or contrary evidence we need to think about? Let's go and look at that. Let's not just draw a line and forget about it because we don't think it's credible. I think there's some lost learning there potentially, and I understand why. I'm not trying to critique people and their decisions. I'm just saying we could learn more. B133221 insufficient helium actuation pressure addresses that the pilot valve opens via helium, so there is a potential failure mode of inadequate helium to drive the pilot valve. Similar to B13316 inadequate blank margin, this mode has been deemed not credible as longer duration thruster firings that valves were opening and closing properly indicated that the valves were staying open for full duration commanded open. Pre-flight analysis shows adequate hold open force margin. Okay, so yeah, okay, so I can see what they're saying. It sounds logically that if there is inadequate pressure in the control path, inadequate helium to drive the pilot valve, there's the potential for that, but the evidence they've got doesn't show that that's a scenario. Okay, fair enough. And there's pre-flight analysis shows adequate hold open force margin. Excuse me. So pre-flight analysis. So if we were thinking about the control structure for this, there is the operational control structure, which is involved in the direct operation of that thing in real time. And then in this case, there is the pre-flight analysis control structure, which will collect information, generate information and control actions, and provide that to other controllers in the structure. And of course, in this case, it says they do some pre-flight analysis, and it shows adequate hold open force margin. So what is the feedback that pre-flight analysis controller has collected, and how has it informed the decisions? And then did it generate any control actions to the operational controller, or is it just for the benefit of the investigators afterwards, the test team? Okay, so B134 prop filter blockage addresses that significant amounts of FOD could reduce or block flow of oxidizer and clog the associated filters. It is unlikely that the thruster lever thruster level filters would have been impacted. It is far more likely that the upstream manifold filters would have been affected by significant amounts of FOD. Degrading PC thrust with continuing hot fire is consistent with the presence of a blockage. However, most thrusters were able to recover during docked hot fires, invalidating this as a potential cause. Okay, so we're talking about this control action path. So the fuel going through the filters, manifold filters. Right, so B14 unstable oxygen state identifies the possibility that the oxidizer, sorry, it's not oxygen, is it? It's oxidizer. Sorry, everybody. Oxidizer, not oxygen. State identity, it could be oxygen, but it's not. Anyway, unstable oxidizer state identifies the possibility that the oxidizer was not capable of providing sufficient reaction. The oxidizer was not of the correct phase density when reaching the combustion chamber. This branch is divided into two-phase flow and helium bubble. Two-phase flow identifies the possibility that the state of the oxidizer from liquid to either gas or solid impacted mass flow rate of NTO oxidizer to the combustion chamber. B1412 two-phase flow is divided into 1411 vaporization, 1412 cavitation, and 1413 frozen. B1411 vaporization identifies that nitrogen tetroxide is heated above its boiling point for a given pressure, turning it from liquid to gas. This would reduce the mass flow rate of the oxidizer to the combustion chamber, negatively affecting the chamber pressure and thrust. Valve body temperature observed near the NTO MMH inlet. MMH, everyone, what is it? Monomethyl hydrazine. Oh, that sounds exciting. Whatever that type of fuel sounds really exciting. So nitrogen tetroxide and monomethyl hydrazine inlet exceeded NTO boiling point at various times during the mission. That's interesting. So valve body temperatures observed near the inlet exceeded the boiling point at various times during the mission. So is that normal? Is it supposed to do that? It may be that that's the design that's supposed to do that. Or it could be that it's not supposed to do that, in which case there's a different avenue of inquiry. This was observed via the node 12 temperature sensor. So this node 12 temperature sensor on various thrusters, so there's multiples of those, is captured below in figure 21, Boeing led CFT combat fitness test. No, it's not CFT, it's a crude flight test. There we go, CFT. Reaction Control System Thruster Risk Chart from June 2024. No clear evidence of reduced thrust prior to tripping FDIR limit, comparing oxidizer fuel temperatures to node 12 prediction. Right. Okay. So we're saying the temperatures observed near the inlet did exceed the NTO boiling point. But there's no clear evidence of reduced thrust prior to tripping the limit. Okay, so this is interesting because if you've got sensory feedback that's saying the temperature is high, is that supposed to result in a particular action by the thrust control system or the temperature thermal control? I think this needs a bit more. Out of all the ones we've looked at already, I think this one sounds like it's. We need to look around this loop a bit more. We need a bit more information. We need access to the subject matter experts to flesh out this loop for this particular topic and try and understand what's going on here, because I think there's something potentially interesting going on here. Especially if they're saying there's no clear evidence of reduced thrust prior to tripping the FDIR limit, comparing oxidizer fuel temperature to node 12 prediction. Because this one sentence, that implies a type of control algorithm, a type of decision making of one or more controllers. And it mentions an FDIR limit, a tripping limit. So the tripping limit is in the control algorithm, the decision making, but the limit itself is based on some kind of belief or process model, which in this case is based on feedback from the node 12 temperatures of the spacecraft. And they're saying here that they've done an analysis with a prediction. So if we did a loop for the spacecraft, and if we did another loop for the prediction and how the prediction affects the decision making, then we might find there's an issue here in the algorithm that the controller has. Perhaps it's a case of it's supposed to shut it down when a temperature is approached or reached, or it's not supposed to shut it down, in which case it shuts it down when it's not supposed to. So there's a lot of potential questions around this. I'd want to, out of all the ones we've talked about so far today, I'd want to dig into this one a bit further. Because as you noticed, all the ones we've talked about up to this point have been about this bit, whereas this one is actually talking a bit more around the other parts of the control loop. And especially if we've got a slide there that's saying there's no clear evidence of reduced thrust prior to tripping the FDR limit. So, well, what does that mean in the context of this loop? Because it may be this analysis is wrong, and they've come to some wrong conclusions about the situation. I don't know that. I'm just hypothesizing. There we go. That's easy for me to say. Right, let's just have a quick break and a quick drink. Have you got any questions? Whilst I'm there, we go. I'll zoom in a bit bigger. Have you got any questions, comments, concerns, compliments, commiserations that you'd like to offer? Please type them in the chat. And of course, if you're still watching this, please let me know where you're watching from. Whether you're sat in the car and your partner's driving and you're listening to this and entertaining yourself, or whether you're somewhere else. The more exotic, the better. And I'm just going to have a quick drink, so just bear with me a second. The live stream seems to still be working. It's not collapsed, so that's good. My camera's not shut down because it's too hot. Fingers crossed it carries on. Everything else seems to be working. So I've got some feedback there. I've updated my mental model. I just want to say it's fantastic to do this kind of stuff. I do this because I think it's really important, and I want to share this experience with the world so that I can help you avoid these kind of problems, or at least if you do have a serious issue, help you to get to the bottom of it and make recommendations and prevent this kind of stuff from happening in the future. So yeah, let's keep moving. So is everybody back from their little refreshments and everything? Let's keep going. So two-phase NTO, nitrogen tetroxide, would increase flow resistance, resulting in a mixture ratio shift, interesting, and reduce thrust. In addition, temperatures downstream of valve seats in the oxidizer flow path to the injector are expected to be higher than those measured at the valve in soak-back conditions. So again, this topic is very much about the control path. And I've just realised I'm busy talking away and you can't see what I'm talking about. There you go. Right, so I've just read this bit here. So two-phase NTO would increase flow resistance, resulting in a mixture ratio shift and reduced thrust. In addition, temperatures downstream of the valve seats in the oxidizer flow path to the injector are expected to be higher than those measured at valve in soak-back conditions. So again, this little paragraph is all about this control path. And where is it? So temperatures downstream of valve seats is sort of the bottom part of this path. And the oxidizer flow to the injector is sort of down here, and then the valve in the soak-back conditions is up here by the sound of it. It'd be nice if there was a diagram, but I appreciate that you're not going to want to put that in a technical, publicly available report. I totally get that. Here we go. So we've got a big redacted bit. It's all black. Can't see anything. B1412 cavitation identifies the possibility that a choking of the flow rate occurred, causing insufficient oxidizer to reach the combustion chamber. Two-phase flow has a lower density due to the presence of gas bubbles and chokes more quickly compared to an incompressible fluid. This limits the mass flow downstream of the choke point. So we've got this figure 23, which is, where is it mentioned? It's not referenced in the text. That's helpful. So a recommendation to update the report. If you're going to stick a figure in, please reference it and explain why it's in there. Here we go. So cavitation model of the RCS thruster. So the same cavitation CFD, so I'm presuming that's computational fluid dynamics. Let's look at the oh, there it is, look, computational fluid dynamics, fantastic. We could talk about software in computational fluid dynamics and whether the software and the models that are used have the appropriate safety integrity requirements to support this kind of analysis. That's a can of worms I'm going to kick over there. Cavitation occurs when flow velocities are locally dropping static pressure below vapor pressure, causing cavitation pockets. This temporary effect was observed during White Sands Test Facility testing. During truncated profile 4, there was also a drop in performance observed in other downhill tests that were run, each resulting in RCS thrust becoming permanently degraded. That's interesting. RCS thrust becoming permanently degraded. Why would that be? Same cavitation model used to simulate steady-state oxidizer flow. Updated geometry shown at right, based on CT scans, computer tomography scans, presumably. CT, it's not in the list. Update the report, put CT in there. From the WSTF thruster, updated model produces expected pressure drop within 2% of nominal mass flow rate with abnormal pressure drop of 240 psi-d. Pardon me, assessing MON flow. MON flow, what is MON flow? It's not in the acronym list, it's not helpful. Assessing MON flow, MON flow, I don't know what that is, I'm not going to guess. Flow rate sensitivity to seal deformation and elevated temperatures. Simulations completed with several poppet seal extrusions represented by different strokes and over a range of temperature. Selected CFD results at 20 degrees. Here's 20 degrees, I'm presuming that's 20 degrees centigrade, maybe that's just 20 C as a test point. I'm not going to comment on that, I don't know. So if we were to do a control structure for this modelling and how it fits into this control path and the decisions about it, then maybe, let's say they did a model, it was 80% representative, let's say, for argument's sake, and then later in the design process, the program, they would need to update the model again, and for various project management decisions they didn't do it. That might explain why later on, we ended up where we are. I'm just sort of, I'm trying to expand the conversation beyond just looking at failures and components. We've got to remember that these components and their installation, operation, everything else is in the context of an operational control structure. But for them to become part of an operational control structure, they must have been subject at some earlier time in their life to the design, manufacture and test control structure. And so if the output of the design, manufacture and test control structure into the operations control structure, if that was inadequate for whatever reason, we have to go back and look at those design, manufacture and test control structures and understand why they behave the way that they did. And when we're using models and making assumptions, how are those assumptions managed and tracked, and how are decisions made, and of those decisions, which ones may have contributed to this? That's what we should go and explore. And again, this could be a mini thread of the investigation to spend some effort to try and understand a bit more. But I'm not getting a warm feeling about that part. I don't know enough personally to be able to comment on it too much. So let's keep moving. So it is expected that B1411 vaporization would be transient in nature. So it's expected that it will be transient in nature. After enough flow has occurred, the thruster would cool and expected performance would return. If the reduction in flow were a result of cavitation, then it would be expected to be semi-permanent, as the change in flow rate as a resulting change of the structure of the valve would likely remain in subsequent thruster firings. The evidence supports this being a contributor to the thruster fail-offs. I think I must have missed something there. So this says it's a temporary effect. But that says there's a permanent degradation. This doesn't sound right to me. I would have thought that if you've got two vapours, two fluids coming together, and they have cavitation and that affects their pressures and the way they perform, I get that. But the RCS thrust becoming permanently degraded suggests that that condition has affected the valve in some way. That doesn't make sense. Maybe I don't know enough about this. If you know, please give me some abuse in the comments and explain to me why a temporary effect would result in a permanent degradation of the RCS thrust, unless the cavitation becomes a permanent feature due to the dynamics, pressures and temperatures and everything else. But if that's the case, then the design of the thrust control system, and particularly the monitoring feedback path, should be designed to detect and deal with that, either to make people aware there's an issue with the thrust performance, it's been degraded, or the control system needs to be controlled in a way that prevents or recovers from this type of effect. This sounds like, out of all the things we've done so far, and I've probably already said this once already, I think this bit needs to be dug into a bit more to understand what's going on with the design, the operations, and why it was designed that way, because that really doesn't sound good to me. But again, I'm a layperson in this respect. I know enough to be dangerous, and sometimes that's good, but sometimes it can be a bit annoying, so please bear with. Okay, so B1413 frozen identifies the possibility of a phase change in the oxidizer resulting in insufficient flow of the oxidizer to the combustion chamber. This would result in reduced thrust. There is no evidence of the oxidizer reaching temperatures below the freezing and causing this to potentially occur. So I'm just going to highlight this bit. There is no evidence of the oxidizer reaching temperatures below freezing. So let's just go back to our little control loop, everybody, our jigsaw piece. I'm hoping by the end of today's session you'll have this burned in your brain. If the oxidizer is in the control path and it is essentially frozen, then what feedback do we have that indicates directly whether that is the case or not? Or is the feedback we have potentially circumstantial or indirect? How do we know as investigators? But more importantly, does the thrust control system know that? Should it know that? Is the thrust control system loop designed to be able to do that? Is it supposed to know that? You know, because if it knows that it's frozen, then is it supposed to indicate to the ground, hey, the oxidizer is frozen, or it's at a particular temperature range? I would guess that it probably does collect that kind of information, and I'd guess that it does provide it to the ground. But whether that information is available with sufficient resolution for the investigators to know either way, I don't know. So again, I think that's a bit of a pet project for somebody to go and have a look at, understand what that loop is, what it looks like, how that might contribute to the investigators or the thrust control system not knowing what it needs to know or reporting what it should. Okay, so helium bubble identifies the possibility that a change in temperature of the oxidizer could result in the helium coming out of solution. The helium bubbles would cause a poor mixture and reduce thrust, Based on computational fluid dynamic analysis, it is not possible for a bubble to reach significant enough size or accumulation to explain the thruster failures and associated degradation performance. So I'm sure that people in the chat are already screaming at their iPhones and saying, "Oh, Simon, well, it's based on a CFD analysis. What if the analysis is wrong? What does that mean?" Well, yeah, exactly. So if we're doing a computational fluid dynamic analysis and we have some models, and those models are based on beliefs that are inadequate or inappropriate or don't represent the real conditions either on the test rig or in this real situation, then of course we might make claims that we don't realise are inappropriate or wrong, and that might give us a warm feeling that is not earned. So we have to be vigilant to that. Anyway, let's keep going. So we've got so we're nearly at the end of section B, and then the next section is environment, and then we're on a different section completely. So what I'm going to do, looking at the clock, it's 19:10. So we've been going 2 hours 10 minutes. Well done everybody for sticking with me this long. So what we'll do is we'll get to the end of the environment section, which is just 2 more pages. Well, 1 and a bit more pages. Sorry. We'll get to the end of this section, and then on the next live stream we'll pick up on the environment section and we'll keep going with that one. Let's have a look. So incorrect. So whatever is under this black box, it doesn't have, or we can't see whether it has a label, a figure number, and it's not referenced in the text. So I don't know what that black box is. It could be it could be a slide like this, but it's not labeled, so I can't say anything about it. So incorrect fuel flow, B2. So incorrect fuel flow addresses the possibility that the fuel flow reaching the combustion chamber was insufficient. This could mean there was insufficient pressure, leakage or unstable fuel state causing an interruption to the reaction occurring in the combustion chamber. So if we know, let's say for argument's sake, we're going to design a thrust control system. And our thrust control system is going to provide some, where is it? We're going to provide some fuel to our combustion chamber. And we know that the provision of that fuel could be affected by pressure, so we don't provide enough pressure or too much pressure. Leakage, so we lose some of this stuff, or it's the fuel itself changes state during that period of time. What do you think that controller would need to know in its beliefs, in its process model, about those 3 things? So we'd need to know about pressure. So logically, from a feedback perspective, we need some kind of pressure feedback, pressure sensor or sensors. Maybe it's so important that we have redundant sensors. Maybe even different types of sensors, diverse sensors. Maybe all of the above. And what about leakage? Is there any type of sensory feedback we might need for leakage? And is there any question over the sensitivity of those sensors? And then, of course, the fuel state and whether it's changed or it's unstable. What type of sensory feedback might we need about that? Is that actually in the design as it is today? Yes or no? Maybe it's a rhetorical question. Is that something that perhaps needs to be in the future to protect against this kind of issue with thrust control? Is that something we might want to think about? Rhetorical question. There we go. So telemetry data across failed thrusters. So telemetry data, there we go. So telemetry data. So this is the feedback I was just pointing at. Across failed thrusters indicates that the fuel was continuing to flow and there was no interruption of fuel into the combustion chamber. It shows the fuel was cool enough and not at an excessively elevated temperature. This is evidenced below in the cooling that was occurring within the combustion chamber, as observed in Figure 10 B1A3 chart demonstrating fuel flow across the injector. So where's Figure 10? Right, Figure 10 is all the way over here somewhere. That one. There we go, everyone. Figure 10. We can't see it. It's gone. So that is a chart that demonstrates fuel flow across the injector. Okay. And what I'm trying to do is stretch your mind and highlight that there is a potential, logical potential, that this feedback that the investigator or the controller is getting, so this feedback telemetry data that updates our beliefs and makes us think that fuel was cool enough, maybe there's an issue with that feedback path that makes us think the fuel was actually cool enough when actually it wasn't. You know, it indicates that the fuel was continuing to flow. Well, what if it was incorrectly indicating? What if fuel wasn't flowing, but it indicates that it was? And that there's no interruption of fuel into the combustion chamber. Well, maybe it indicates there's no interruption, but actually there really was. Now, of course, there are other feedback paths, data that are available to the investigators, which might show actually that feedback path that we're focusing on is actually working and perfectly fine. But we need to ask that question. We can't just assume that the data is telling us everything is fine, so everything is fine. We have to trust but verify. I hope that makes sense. I don't want to sound like a paranoid, I'm super paranoid, but this is the logical method that we're following here. We don't want to assume, we have to trust but verify, we have to check. And be open to the possibility something really weird might be going on. And it's only weird because we don't have the big picture. And what we're trying to do using this method is try and uncover what that picture is, systematically. Okay, so B3, failed combustion chamber, a ZOT or other event. So ZOT. Oh, look, there it is. Look, ZOT is in there. Fantastic. So ZOT means, or is it a ZOT as opposed to a ZOT? Come on, give me some abuse in the comments. So ZOT, hot spot combustion. A hot spot combustion or other event that causes a degraded state of the chamber. So we're talking about the control process here. So what is it about the control process that could contribute to this misunderstanding, inadequate feedback? It could be there's a problem with a problem with the chamber itself. So a ZOT, hot spot combustion or other event that causes a degraded state of the chamber can possibly cause a failed combustion chamber, affecting the overall capability of the thruster. So each of the thrusters has their own combustion chamber, of course. On-orbit inspections did not show any damage through image resolution, although image resolution is limited. So again, if we're talking about on-orbit inspection, so this is the investigator or the ground team, they're receiving resolution-limited information. The borescope images from the ground during WSTF inspections, so this is a different feedback loop providing similar data, are of a much higher fidelity than the images taken on orbit. The borescope images were positioned in the throat itself, while the cameras on orbit were hovering on the outside of the nozzle. The data from the docked firings demonstrated that the thrusters had somewhat recovered, which would not have occurred in a failed and/or degraded thruster chamber. The combustion chamber is not considered to be a cause or contributor. Okay, so these pictures here, these are external pictures looking at the thrust chambers. I mean, you can see the quality of the pictures. They're not very good on here, but they might be better in the original. So there's 2, 4, 6 thrusters there that they inspected. Yeah, okay. So B4, failed throat. So throat erosion investigates whether the thruster throat may have become degraded and/or failed because of thruster operations. Similarly to the combustion chamber, on-orbit inspections did not indicate throat erosion. It is possible that some throat erosion may have been missed during the on-orbit inspections due to lower image quality and ability to get a closer image. So again, this is sort of hinting at, if we were going to design the control structure for on-orbit inspections, so this feedback path, what would we want that feedback path to look like? Well, of course, we would want the best possible quality data, quality feedback, early and fast as possible, wouldn't we? So has that been considered as part of the design? Has ground control thought, hey, if we have to do on-orbit inspections, we need this kind of capability in orbit? Rhetorical question, maybe. But it goes back to the high-level safety constraints. So the high-level safety constraints that the control structure must enforce are, first and foremost, eliminate the hazard. If you can't eliminate it, deal with the consequences, and recover from the situation, respond to it and recover from the situation. In this case, we're talking about, well, what type of recovery do we need? Well, we need some form of on-orbit inspection capability that provides us with the sufficient level of detail and resolution and quality and all of those other good things in all the different bands that we could possibly want. Maybe we need an X-ray machine in orbit, something like that, so that we can look at these things and provide feedback to the decision makers so they can make better mission and safety related decisions. Okay, so collected flight data is not indicative of an impactful level of throat erosion. However, minor throat erosion would result in a minor reduction to the PC, which could have dropped an already degraded thruster below the FDIR limit. The docked hot fires demonstrated that the chamber pressure recovered. This would not have been possible if the throat had significantly eroded or there was a total loss of the throat, causing the observed reduction in the PC. I think PC's combustion chamber pressure, if I remember correctly. PC, PPPPP, it's not in the acronym list. How handy. Fantastic. Put it in the acronym list, please. It should be noted that due to the smaller thruster firings of the Starliner vehicle in comparison to nominal ISS thrusters, so I think that's the International Space Station thrusters, and the position of the thrusters in comparison to the ISS Space Integrated Global Positioning System Inertial Navigation System, SIGI, there is an error rate of approximately 14%, which may hide minor throat erosion. So here we go. We're talking about what is the feedback path that's providing us data, and does it have any errors in it? And this says there's 14% of errors. So there we go. And again, the ISS and all that other good stuff is not designed, I'd assume, for doing these kind of anomaly diagnostic activities. So maybe there's a requirement there that in the future there is an on-orbit diagnostic capability. Maybe there's I'm going to push the boat out there, so bear with me. Maybe there is a requirement to create a space-based, what's the term it used? Space-based on-orbit inspection vehicle. And you can have this one for free, everybody. There you go. On-orbit inspection. So you need a spacecraft that is capable of doing on-orbit inspections. And those inspections are capable of certain resolutions, timing, accuracies, all the other good stuff. And so you could use that spacecraft to basically do on all these on-orbit inspections. But of course, you might say, yeah, but Simon, what's the probability of needing to do that? And I think when we start talking about probability, it's like, well, we've got these big expensive spacecraft that we've put up there, and it costs a lot of money to get them there and design them and everything else. Maybe it would be a good idea to have a rescue and recovery capability, like a lifeboat, a space RNLI perhaps, that can go up and recover things and do some on-orbit inspections. I don't know. Just an idea. It's been a long day. It's like 2.5 hours. Okay, so the docked hot fires, I've read all that. The error rate 14%. The removal of the thruster via FDIR was not the failure. Ooh, hang on a minute. The removal of the thruster via the FDIR was not the failure, but the degradation of the thruster and its capability to produce thrust. It is possible that minor throat erosion incapable of being viewed with the available imagery did contribute The degradation of combustion chamber pressure, thus throat erosion is an unlikely contributor. Okay. And then finally, B5, failed nozzle. A failed nozzle, a damaged nozzle, or a cracked nozzle would potentially affect the thruster capability. There was no damage observed on the thruster nozzles during the on-orbit inspections. Okay, so where's the conclusion of that? You should say, well, we don't think that's a problem either. Okay, there we go. Right, so we've done a lot today. We've done really well to get through all this. So thank you so much for your attention. There is something I need to show you on my website. Actually, let me just get this link. I'll stick a link in the chat. There we go. Right. So I'll just share my screen again. Right. So what I've done, and in anticipation of the workshop we're going to do together. So this is going to be a free workshop on Zoom where we're going to get together live and we're going to talk about this case study together as a group. Now it's going to be a free workshop. And essentially what I'm going to do is once I've finished the investigation report, I'll then set a date for this workshop, maybe a couple of hours, maybe half a day, something like that, so we can really talk about this to death in detail. And it's essentially a free event. So I'm going to stick the link in the chat. So paste, there you go. If you go to that link, you can stick your name on the list, and then when the time comes, once I've finished all of these live streams and finished the report, I'll put some slides together, build a control structure model or a few of those. It sounds like there's probably 3 or 4 I need to think about. So one is about the operations control structure, one is about the investigation control structure, and then one is about the design, manufacture and test control structure and how they fit together. And so we can talk about those through, and you can ask as many questions as you want in that time. And I hope that it's really helpful and beneficial to you and gives you some food for thought, and perhaps build your confidence so you can have a go at doing this stuff yourself. So if you go to the link in the chat, in fact, actually, I can click on there. Look at that. If I press that button, there we go. So there's the address, whiteley-safety.co.uk/260703 waitlist-LP landing page. I should come up with something a bit easy to say, but if you go to that address, click on the link, stick your name and email address in there, I'll add you to the wait list, and then when I've finished this, we can get stuck in. So I hope that was helpful. Thank you for your attention, and I look forward to seeing you on the next live stream. Take care. Have a good evening. Bye-bye.